Do you have an existing web app that already uses Postgres database and would like to add Google-like search with quick, accurate results with highlighting, spell correction and dynamic summaries? For instance, searching for Albert but without Einstein, life, will give you movie Defending Your Life with Albert Brooks and quotes from Albert Camus and Albert Schweitzer about life. Typically, what's meant by full-text search would entail employing external tools, most likely based on Lucene's search and indexing library, like Elasticsearch, or some third-party cloud search provider like Algolia. So you need to manage additional infrastructure or pay someone to do that for you. Before investing time and money, maybe you can do more with the tools you already have. In this video we'll have a look at Postgres full-text search features which may prove to be sufficient, especially for small and medium-sized projects. Providing full-text search usually means some or all of the following features. Ranking. Results have order based on how close they match for what you search for. Stemming. Words are reduced to their roots so that searching for example run would also find running. Synonyms, searching for car would also find automobile. Phrase matching, similar way in quotation marks, does not equal way similar. Spelling correction, misspelled sometimes would offer you a suggestion, did you mean sometimes? Unlike relational model, which thinks in terms of entities and relationships, full-text search engines generally think in terms of documents. Postgres full-text search is no exception. For demonstration purpose, we'll go through broad overview of the indexing and searching process in Lucene, which is core component of Elasticsearch. Process starts with acquiring raw content from which we are building a document, analyze it to be able to add it to the index. This is the indexing phase. User performs search and run queries on created index, which enables under-second accurate results with all the feature of full-text search engines we mentioned previously. This is the search phase. To demonstrate Postgres full-text search features, I've prepared a project for which I'll leave a link in a video description. For starters, we have a Docker Compose file which defines Postgres as a service and loads initial data with famous quotes and movies and actors to simulate two different data sources you might have in your application. We'll start our database by running Docker Compose up. And the first time you'll start it, you'll see database rows inserted with the data I've prepared. Once the database has started, we'll open dbeaver and create new database connection. Postgres with the database type, host is localhost, database name is FTS for full-text search, username is user, and password is pass. Test. Finish. And we can open new SQL editor. If something goes wrong with your database, you can stop the Docker Compose service by running Docker Compose down -v to destroy the volume, and then start the service again. This time I'll start it with in detached mode by running Docker Compose up -d. As for the existing data and tables, I've prepared quotes table which has quotes from famous authors, vQuotes view which has also tags belong to those quotes, movies table with lists of famous movies, and vMovies view which has actors starring in those movies and the genres movie belongs to. Let's first discuss regular text search operators in Postgres. First, there's the like operator. And with like operator we can use the %sign to signify 0 or more characters. And we don't care what they are. In this case, we are searching for the string that begins with any and has any number of characters after that. When we execute the query, we see that we get the quotes that begin with anyone, anyway, anybody, as well as any space full. Like operator can also be specified with double tilde sign, so executing this query will give us the same results. Besides that, like supports underscore character, which means one and exactly one character. So with this query, we are specifying any number of strings, then the string needs to have on, then it needs to have one character, we don't care what it is, and it needs to end with a dot. So if we execute this query, we get the quote that begins with anyone and finishes with strong dot. So strong is ON and the one character is G. Besides like, there's also case insensitive like operator, which is I like, and this gives us, even though we specify lowercase any, it gives us strings that begin with uppercase and A as well. And the equivalent operator for I like is double T then star. Besides like and I like operators, there are regular expression operators, which are just one tilde, and this gives us the string beginning with any, and case insensitive regular expression operators, which is tilde star. Regular expression operators are extremely powerful and they are topic for themselves, regular expressions are. These text operators are powerful and can get you pretty far, but are missing some features of the full text search, like ranking. They treat all results equally. There's also no concept of word, and as such you can't have word normalization, word root, or word synonym. To support full text search, Postgres follows philosophy of full text search engines like Lucene in that it has two major parts. One takes care of analyzing text to create documents that represents text in processed form, which is furthermore suitable for indexing, and other that serves for searching, representing a predicate for documents you're searching on needs to satisfy. These two parts in Postgres are represented by two new data types: text search vector, tsvector, that represents document in form suitable for searching, and tsquery that represents the predicate, the query. To drive the point home that these are two new data types, we'll create a table with columns based on them. Now is also a good time to remind ourselves that for text, Postgres supports char data type, which is fixed length blank padded string, varchar with a limit, which is variable length with a limit string, and variable length unlimited string, which is text, is the same as varchar without the parentheses. And tsvector and tsquery are just new data types, and we can create two columns based on them, just as the normal string columns. To convert text to tsvector, Postgres provides a built-in function toTsvector. Let's look at the quote with the ID of 1112. All the darkness in the world cannot extinguish the light of a single candle, by St. Francis of Assisi. If we run toTsvector on a quote, we'll see we get sorted array of lexems with positional information, which we'll see in a short while is optimized for searching. All the darkness. Darkness is a third word in a quote. It has been shortened to dark and contains positional information of the token in a text, number 3. If I were to concatenate dark to the quote and run the query again, we see that dark contains two positional information now. It's contained as a third and as a last 15 token in a string. There are two overloaded functions to tsvector, one receiving configuration as the first parameter. If we left it out, in our case, default configuration is used. In my example, English. And we can explicitly add it as a first parameter and get the same result. If we connect to our Docker database container by running docker exits -it container name bash, we can use PSQL, and the schema name is fts user is user, to connect to the database terminal. In terminal, we can run \d command to get a list of text search configurations our Postgres installation came with. And in there we see English as well as host of other languages, and we see simple configuration as well. If we go back to dbeaver and run English configuration on our quote author name, we'll see that auth is removed from the tsvector. In cases where we are dealing with person names, it might be more appropriate to use simple configuration. Simple configuration does not remove anything, but only tokenizes a string and leaves words as they are. Auth is removed in the case of English configuration because it's considered a very common word that has no value in search. In terms of search lingo, it's considered a stop word, and different stop words get removed based on different dictionaries. If we get back to our Postgres database container and run pg_config --share there to get the location of our shared directory and cd into it, we'll see it contains ts search data directory. In there we'll see different stop words for different languages. So we can just cat English stop words, and in there we'll see all the words that get removed. And if we grep for off, we'll see that off and off with two Fs will be removed as a stop words. We can add or remove words from this file to modify stop words being used for different languages. Let's cat stop words for German language, and we'll see different words like will, wir, wird, wirst, etc. If we get back to dbeaver, we can run German configuration on German sentence was machst du gerade, and we'll see that was and du were removed as stop words, and machst and gerade were shortened to their gerade and macht form. German language has umlauts, which are these special characters above letters, and some other languages have them as well. And Postgres provides unnacent extension, which you can create, and then it will remove those special characters by using unnacent function and provide better search results. We can see when we run to Tsvector on Übung macht and Meister that Übung is just shortened to Übung without the umlaut. To recap, Tsvector is first parsing text into tokens, result of which you can see with tsparse function. On our example, we see that tsparse breaks our quote into a list of tokens, all space, the space, darkness, space, in space, etc. And then each member of the parsed list is fed to dictionary, which is a function that accepts token on input and returns array of lexems, null if token does not get recognized, or empty array for stop words. We can use tsLexsize function to test the output. Some dictionary, in our case English stem, would return for appropriate token, in our case darkness. If we run the query, we see that lexem dark would be returned. If we run tsLexsize on a stop word like is, we'll see that an empty array will be returned. If you want additional information about how the words are turned into lexems, you can run tsdebug function, and in there you'll see what dictionary is being used and how the word will be rendered. We used English stem dictionary, and you can get a list of installed dictionaries when you go to PSQL terminal and run \d FD, and in there we'll see the dictionary names. Second part of the Postgres full text search world is tsquery, which is a textual data type for querying with Boolean operators and or negation and grouping operators. To convert text to tsquery data type, Postgres provides a couple of conversion functions. Most basic one is to tsquery, where we can specify text separated by Boolean operators. In our second example, we would search the text that contains word world and does not contain word light. To tsquery function does not know how to convert space separated text to tsquery data type. It will throw an error. And in order to do that, Postgres provides plain to tsquery function, which converts space to ands automatically. In our quotes example, we might search for a specific phrase. In other words, we'd like to preserve the information about word order. And in order to do that, Postgres provides phrase to tsquery function. The result are words separated by the distance operator. So in this example, extinguish must follow after the word cannot extinguish. Number inside the operator instead of the minus specifies how many tokens are allowed between words. So extinguish and then 2 tokens, second token is light. Extinguish the light. The is counted as a token. Similarly with dark and 3 tokens and a world. Darkness in the world. And finally there is web search to tsquery, which we can use to enter Google-like queries with minus, phrases, etc. And for our web application, we can use this function to convert user search string to tsquery search predicate. In this example, we are searching for text that contains word cook and bake, but not the word captain, and also phrase nothing or something. And we can notice that nothing and something were trimmed down to their stemmed versions, to their root, noth and someth. And finally, the way you combine tsvector and tsquery to perform searches is with the double @ operator. And you say tsvector double @ tsquery. query. In our example, we are searching for I'm riding string in a nice day for a car ride vector, and it does produce results because I'm riding is trimmed down to ride, and a nice day for a car ride is car day nice ride. Double at operator also allows reverse positions, so in this example we are searching for tsquery double at on tsvector, and we are searching for I'm riding a bike in a string a nice day for a car ride, and this time it won't produce results because we are not riding a bike, we are riding a car. So we'll comment out this part. Another useful thing you can do is use the colon star operator to search for the beginning of the words. So this will search the word that starts with RI and ride does, and we can also add D, and we can also add E. It will all hit. It will produce positive results. As far as for operators on tsquery and tsvector themselves, I'd like to point out the concatenation operator that works on tsvector, which would concatenate two tsvectors together, and the AND operator on tsquery, which specifies that both predicate needs to be satisfied. If we run the query, we get the results. A nice day for a car ride does have the word begin with RI and also has the word day. In our more realistic example for quotes, we are joining quotes with quote tags and tags to produce results, and we are producing vectors for our quote, for our author and our tags. And it's important to think of null values for tsvector and coalesce them, so we replace them with empty strings. Since full text search likes to think in terms of documents, not columns, the first thing we can do is concatenate our three tsvectors to produce a single document we'll later search on. We'll usually construct our full text search tsvector document by concatenating a couple of fields, in our case quote, author and tag. We can assign different weights to different parts of the documents by using labels A to D. Labels are equivalent to coefficients 0, 1, 0, 2, 0, 4 and 1, with A being 1 and of the most importance, 10 times more important than D. You rank different parts of your document by using the setWeight function on your tsvector. We can get a hold of what various tsquery's predicates have on the same tsvector by using the tsrank function. In our example, we see that the rank for dark and mind is 008, which is higher than rank for just dark, which is 006, because our quote has both words mind and dark. So the more occurrences the words in the tsquery the vector has, the higher the rank. There is also the tsrankcd function, which stands for cover distance, and it takes into account how close are words. The closer the words, the bigger the rank. We can combine our tsrank functions with setWeight to give different weights to different parts of the document. So in here we assign no weights and we get 0,1 rank. In our second example, we'll assign weight A both to author and quote, and we get different rank. And finally, we'll assign weight B to quote and weight A to author, and we get the third rank. To conclude, by assigning different weights to different parts of your document, you can influence ranking user search query has, and then order by tsrank to first show most relevant results. I'd also like to mention one useful function for web searches, tsheadline, which tags found results. In our case, we were searching for become dark, and become and dark were tagged with B tag. B tag is the default tag, although we can change that by using additional configuration options. In our case, we've changed the B tag to emphasis M tag. We can then use tsLn function and tags it produced in our web user interface to mark to the user why did its query hit on the results we've returned. Couple of warnings though, tsLn function operates on a clean text, not tsvector, so it can be slow, and I found it sometimes returns unexpected results. Our searches so far didn't handle synonyms. For that, we'll need additional synonym rules configuration placed in a PG share directory. Postgres comes with an example that only has synonym for one word. So it's a x synonym sample.rules file, and it has synonym for supernova, which is SN, SNE, and 1987A. To use synonyms, we'll need to go through a couple of steps. First is to include the extension, then to alter our text search dictionary with sample rules, and then to alter our English search configuration to include not only English stem dictionary but also Xsyn. And then we can run the select. And if we look at our query results, we'll see in our tsdebug function that Xsyn and English stem dictionary is used, and supernova, SN, SNE, and 1987A synonyms are used for the word supernova. And if we vectorize supernova and search for SN, it does produce rank, it does produce results. If you want correct synonym search in your Postgres full text search, you'll need to place valid synonym rules file in Postgres shared directory and alter the text search configuration as we did with the sample file. Running queries on Tsvector on table with large number of rows will be slow. To improve performance, you'll need to create an index. Your options are GIN, General Inverted Index, which means that each lexeme has one entry and it's larger, slower to update, so better on less dynamic data, and is recommended for Tsvector columns. The other option is GIST, General Index Search Tree. It's lossy index, which is smaller but slower, as it can produce false positives, so Postgres needs to go back to row to determine whether it should match. It's better on fewer unique items. I'll also mention that Russian developers that mostly develop full-text search features in Postgres are also working on extensions with additional index types named after drinks, like rum and vodka. Rum index is like gin index with additional information about word positions and can calculate rank inside without heap access. Let's go to a couple of real-world examples. If your full-text search requirement is based on only one table, like in this example quotes with the quote and author columns, one approach you can take is to add additional column that is always generated as a result of calculation on dependent columns. In this example, we are adding FTS-doc column that is a Tsvector type and is generated always as, and it's stored, and we base it on our two other columns. So we add it to our table, and then we create GIN index on the newly created column. If we now explain and analyze the query that uses original columns quote and author and queries for the string little, we'll see we get a sequential scan. Versus if we explain analyze the same query on the newly created FTS-doc column, we'll see we have index scan. On a newly created column, our index is working. So for a simple full text search that's based on one table and couple of columns, newly generated always as column and index on it is one of the options you can go with. More realistic example is if you have couple of tables you want to search on. So let's say you have forum and blog on your website. To simulate that situation, I've added quotes table that has data about authors, quotes, and tags about quotes, and also movies table that has data about movies and also actors and genres movies belongs to. For movies data, we create Tsvector from title, description, and movies meta, genres meta, and for quotes table from quotes title, quotes description, and quotes meta, which are tags about quotes. And we union all, so we combine both data sets to create materialized view. Materialized view is database object that stores results of a query but needs to be refreshed as underlying data changes. Firstly, to make queries on our materialized view performant, we'll also create GIN index on the Tsvector column. To keep our view in sync with our multiple tables data, we'll create a trigger function that will refresh our materialized view concurrently. We'll need to call our trigger function refresh FTS documents on CRUD operation of every table our view depends on. In our example, I'll just show how we call the refresh FTS documents on the quotes table after insert, update, or delete, or truncate. In order for trigger to be able to perform concurrent refreshes on our FTS documents materialized view, we'll also need unique index on the view. In order to make sure that materialized view is getting refreshed correctly, we'll insert one additional quote. So if we select current data from our quotes table, we see that the highest ID is 2999. And similarly for our FTS documents materialized view, the latest quote is quote 2999. We'll insert famous quote by Phil Carlton. There are only two hard things in computer science: cache invalidation and naming things. And we'll give it an ID of 10,000 to make it obvious. If we select from our quotes table, we'll see 10,000 ID row inserted. And if we select from our FTS documents and search for ID of quotes 10,000, it's there. Phil Carlton quote is correctly refreshed in our materialized view. Now that we have our materialized view, we can construct select that will perform search in our web application. $Q represents string user will input in search box. First, we'll use double-at operator to match our Tsvector column to user query, and we'll convert the user input to tsquery data type by using web search to tsquery built-in function. We'll use tsHeadline function to mark what was matched in our columns by user query to be able to emphasize it in our web user interface. We'll use tsRank function to rank the results, and we'll order by ranking to display, in this example, only 10 most relevant hits. So, for example, if we execute a query and search for Friedrich, we'll find quotes by Friedrich Nietzsche. If we search for phrase "kills us makes us stronger," we'll get a single Nietzsche quote, the famous one, "that which does not kill us makes us stronger." We can also construct more complex Google-like queries, Albert minus Einstein life, which should find us something that matches Albert and life, but not Einstein. And indeed, we get a match with movie with Albert Brooks and quotes with Albert Camus and Albert Schweitzer. Our FTS documents materialized view provides us the basis for search, but won't cover misspellings. For that, we'll need to use additional PG trigram extension. PG trigram extension generates 3 characters engrams based on Markov chains. Now that we have PG trigram extension enabled, we have available show trigram function. And if we run the function on to and who, we'll see what it produces as results. It breaks words into an array of 3 characters: the space W, space WH, HO space, and finally who. We can now compare how similar 2 words are by seeing how many trigrams they have in common. The concept of similarity is explicit in trigram extension and provided via similarity function. So let's see how similar are a couple of words. Something with capital S is completely similar to something with lowercase s. Something with misspell something without E are similar. Something and unrelated are not similar, and something and everything are similar, but less similar than something and misspelled something. There are additional operators and functions PG trigram extension provides. And there are the % operator, less than, minus, greater than operator, and show limit function. As a result of our query, we can see that the show limit function returns default breakpoint of PG trigram extensions for words to be considered similar, which is 0.3, and we can change the limit by using the set limit function. A less than, minus, greater than operator returns the number of how similar the words are, in this case 0.41. Since the number is greater than the limit, the words are considered similar, which is something that the % operator returns. To provide the user with misspelling suggestions, we can use the less than, minus, greater than operator on a list of words we have and something that the user entered, and order by the operator descending to give the user the most similar words. Now the question is, how do we get to the list of words we have? And we have the FTS document materials view, which has the columns we need, and we'll vectorize the columns and use tsStat function to give us list of different words. This can be the basis for a new materialized view, FTS words, which we'll create, and we'll create a gin index on the words by using gin trigram options. Gin trigram options is something that PG trigram extension provides. And finally, to provide user suggestions, we'll select on FTS words materialized view. We'll only search for words that are similar based on the limit, and we'll order by the factor to first provide most similar words. So if we search for something misspelled, we'll see we'll get something suggestion, something so, soothing, thing, shining, nothing, bathing, etc. In our web app example that we'll create shortly, we'll first try to search on FTS documents, and if you don't get any hits, then we'll try to search on FTS words and offer user similarity suggestions. I've created a simple Spring Boot web app that uses concepts we discussed previously. First, it tries to search on the FTS documents materialized view. If it doesn't find any results, it tries to offer user misspelling suggestions. To provide user misspelling suggestions, we just select on FTS words materialized view and order by similarity factor. And in order to provide normal search, we select on FTS documents where we have our Tsvector column, and we try to match it with the user predicate query that we convert to tsquery with web search to tsquery function. Source code for the application will be in the video description. If we open our app, we'll have two search fields, one where we need to explicitly hit the button to filter, and the other one that will filter as we type. So if we type in our little search field, let's say Albert, we'll get Albert Einstein quotes, and we can select certain quote to get the details for it. If we try to search for Albert in our big input, we'll get quotes and movies with Albert in them, like Albert Einstein and Albert Brooks. And we used Postgres tsHeadline function to tag and emphasize Albert to make it obvious to users why certain results are shown. For more complex search, we can remove Einstein and add life, and filter based on that to get only quotes and movies with Albert but without Einstein, and they are about life. So we get a movie Defending Your Life with Albert Brooks and quotes from Albert Camus and Albert Schweitzer. And if we click on the appropriate movie, we'll get details about it. If we search for misspelled word, like sometimes without the E, we'll get a list of suggestions. Did you mean sometimes, sometimes, sometime, or times? And if we click the first suggestion, we get the quotes and movies with sometimes, corrected word. This concludes our showcase of Postgres full-text search functionality, and I believe we showed it indeed has capable features that you'd expect from full-text search engine, and will be sufficient until you need something more if that day ever comes.